If you want to know how I created a fully room scale IK body in Unreal Engine 4 for use with virtual reality, then you have come to the right place. So let's put the long intro aside and jump right into it. Okay, so first things first, we're going to head over to the Marketplace tab and search for Locomotion. The Advanced Locomotion system should pop up, which we're going to create a project with. I'm choosing Unreal 4.24 for the purpose of this video, and I'm naming my project Example IK. Next up, I'm launching the engine to create yet another project, which will be a game project with a third-person template. When the project finishes loading up, we select the mannequin folder and right-click to migrate the folder to another project. We will browse to the content folder of our previously created project and click OK. Now we can navigate back to the project we created before and add a few folders. We had one for levels and one for materials, and in the levels folder we create a new level called Demo Level. When the level opens up, we navigate to View options on the right to enable Show Engine Content. Then we first place a skylight into the level. Next, in the search box on the left, we then search for the word sky. We can then navigate to Engine Sky and drag the engine's default sky sphere blueprint into the level. We remove our search and start building a basic level by adding a simple cube mesh followed by a directional light. In the sky sphere, we can then select our new light to set it as the sun. Next up, we navigate to our materials folder and add a new canvas render target. We name this T_mirror. In its settings, we set 2048 for both X and Y and then create a new material named M_mirror. In the material editor, right-click anywhere and search for the texture sample node and the text chord node. Connect the text chord node to the sample node and set the texture sample texture to T_mirror and connect the sample's RGB to emissive color. Save this material and exit the material editor. Now get back to the level and drag in a plane. Rotate it to face forward as seen in the video and drag in a camera actor. We're placing the camera actor in the plane and assign our T_mirror texture to its texture target. We then drag our material onto the plane and rotate the plane as required to create a simple mirror effect. Next, we're adding a blueprints folder and are creating a new pawn class called BP_VRPlayer. Once opened up, we're adding a new scene component and calling it VR_root, as well as two motion controller components called motion_controller_L and _R respectively. Keeping in mind to set the right controller to utilize the right hand by setting the correct motion source. Next, we add a skeletal mesh to the root, set it to be our mannequin we imported earlier, and detach it from its parent in the construction script. Then we execute the console command stereo on the event begin play and set the tracking origin to floor. Finally, we create a new function called calculate movement. What we're trying to do is to accurately capture the movements of the player in real life and mimic them in the game. So in order to do that, we have to properly animate the body and place it on the right position in the scene. Now, the first thing we have to tackle is to figure out how the player is moving in real life so that we can make the body follow and animate accordingly to what movement the player is performing. So if we have the player facing a certain direction and then moving to another direction, to another position, then we need to know that, okay, the player started in position A, moved to position B in a certain time span, meaning that we can figure out the movement direction and velocity. If we have the movement direction and velocity, we can animate the body with a certain animation based on the velocity. and we can move the body along with the player smoothly. So in order to do that, we're going to have to create functions for tracking the player. First, we drag in the camera and get its world transform. Then we create a local variable, call it current camera position, and set its type to transform. Then we right click its input pin to break it, and once again break the resulting pins for the position and rotation, and drag in the X and Y and yaw pins from the current camera position. We don't care about the other values for this. We then create a new function called getDistanceMove and add two float inputs being current X and current Y. We then right click and get a distance node, break the pins, and add an output float called distanceMoved. We drag the X and Y into the distance node, get our last camera position, for which we have to create a new transform variable, break it, and then use the X and Y from there as our secondary X and Y for the distance calculation. We can then use our new function to get the distance moved and set it as a local variable in our calculate movement function. Next up, we do basically the same, but we get the distance traveled by rotation. So we create a new function and set current rotation as an input. We then create a float output called distance rotated. Then we split the struct pin from the current rotation, drag in the last camera position, and break those pins as well and subtract the yaws from these two rotations. Finally, we get the absolute value of this and return this as the move distance. Negative movement can be seen as walking backwards in positive amount of meters, hence the absolute value we want to total distance travel. We also drag this new function into our movement calculation and set its output as a new local variable. Next up, we will need to create some thresholds. This is required because what may happen is we can have our player standing somewhere quite casually, not really moving at all, but moving the head just a slight bit to the right, for example, maybe just 3 centimeters. So a 3 centimeter movement does not mean that the person has taken a step to the right. It is simply a slight movement of the head. So we need to create a threshold so that when either rotating or moving the HMD a tiny bit, we do not play a turning animation when turning the head around, or we do not play a walking animation when slightly moving the HMD, just a few millimeters or centimeters or whatever. So in order to ensure that doesn't happen, we will create these thresholds. So we create a new flow variable called movement threshold and one called rotation threshold. Then we add a branch. We then compare whether another XY movement and or rotation movement has passed these thresholds. We do this for both individually because you can, for example, rotate in place, causing you to move without changing XY positions, in which case we still want to update our in-game character's animation. We plug these checks into our branch with an OR statement and we add a sequence. Then create a new function called getBodyRotation from HMD, which will simply return the HMD's world rotation minus 90 degrees to fix the offset caused by the skeletal mesh in regards to the camera direction as seen in the viewport tab. So we return this rotation, not going over every step too much as you can see it in the video more clearly, but still paying attention to the fact that we can make this function pure as it doesn't require any execution pins. Then we move on to the next function called getBodyOffset. This function will return a position a bit behind the camera to prevent clipping. So we drag in the camera, get its world transform and drag out its yaw. Once again, we subtract 90 degrees and make a new rotator. And we then get the right vector of this rotator, multiply it by -20, and add this to the camera position, effectively subtracting 20 units in the camera's direction off of the camera's position. Then, since the skeletal mesh's origin position is its feet, we subtract a little less than the model's height to position its eyes on the camera height. I created a variable called player height for this. Then we return the resulting location and rotation to get the correct position for our skeletal mesh. Next we return to our movement calculation and get this offset. We also create a transform variable, name it body target position, and if the threshold check is true, we set the body offset result to be this target position. Next we get the last camera position and the current one, as we're going to figure out the direction the player has moved in. We first get the forward vector of both positions, then add some make vector nodes to which we connect the x and y, and we normalize this output vector. Then we add these two vectors together, multiply them by half or divide them by 2, and go back to the position nodes to break the location. So we use the x and y locations only, so break and make those vectors and normalize them as well, and then finally subtract them from one another. Then we get the dot product and cross product of these vectors, a cos d the dot product, and we will add a little check to see if the cross product z value is above 0, which we will use to multiply the a cos d result with either 1 or -1. We then select this whole chunk to collapse it into a macro, name the macro getDirection, and create a float output called direction to connect this all to. This effectively gives us the direction in degrees in which the player moved between these points, or so a couple Google results told me. We assign this direction to a local variable and then update the last camera position with the current one. Now, in case you made movement direction a local variable like me, which you probably did because that's what I showed, we have to quickly make that a global variable as we need it in animations later. The same goes for movement speed. Then we set this new variable to the direction we just calculated, and next up we go for the movement speed, which is the distance moved plus the distance rotated divided by the time since the last update, or basically the tick. Then we just follow what I do in the video quickly to fix our macro not being able to read our local variable. Then we're going to do some stuff when the movement thresholds aren't met. If this is the case, then we're going to check if the body is in the desired position yet. If not, we're slowly moving it there in a smooth motion. And if it is, well, we're basically done and don't need to do a thing. So if the body has already arrived, we set the movement speed and direction to 0 again so there won't be any animations playing. And we also add a new variable called alpha and set that to 0 here as well. If the body isn't in the right place yet, we will use this alpha to lerp, so we f-interp to constant the alpha over time based on the movement speed, and use the resulting alpha to lerp our body's position. We set the f_interp constant to 1, and once this is all set, we move the actual skeletal mesh to the desired transform using the set world location and rotation node. With this all done, we can have a quick look at it so far by dragging our player into the level, and don't forget to hit compile beforehand. And we also have to go back into the player blueprint and execute our movement calculation every tick. It's also important that we set our thresholds to some value. I go for 1 here for testing, and later we can set some real values. And if we then have another look, you see the player standing quite high up in the air, which is due to not setting a player height yet, so the character's feet are effectively right on top of our HMD position, so quickly set a value and then the player is roughly hovering on the ground as intended. So, it's about time we do something about the legs clipping through the ground when the HMD is closer to the floor. To do so, we're going to need leg IK. So firstly, however, I'm going to quickly clean up the blueprint a bit by adding a comment to the code we added so far. Then we will drag out a set world location and rotation node from a skeletal mesh and connect our branch to it. We will use this to always set the Z value of our character even when a movement threshold isn't met, and this allows you to perform smooth crouch movement at all times. Now we exit the editor, give our Z updates a quick test to see if we move along smoothly, and finally navigate to Content, Mannequin, Animations, where we will create a new animation blueprint for our character. We select a UE4 mannequin skeleton when prompted and name this blueprint ABP_VRPlayer, then save it and jump right in. So first we drag out delta time and promote it to a variable which we name dTime. Then we add a sequence. We try to get the pawn owner, if valid, and promote that to a local variable as well. Next we get the pawn we just saved and attempt to cast it to our BP_VRPlayer to be able to set our character as a variable as well. Next we create a function called footIK in which we use our stored player to get our skeletal mesh and drag out 2 getSocket location nodes as well as a getWorld location one. We set one socket location node to footL and the other to footR. If you use a different skeleton, make sure to move to the skeleton view and find your foot bones as shown on screen. Now we create a new function called traceGround. The input for this will be a vector called footLocation. Then we add a line trace by channel and drag out a plus and a minus vector modifier as we're going to define a range for our trace which starts a bit above the foot and ends a bit below the foot. So we're adding 200 and subtracting 200 on the z-axis to get a trace of 400 units. If you spot a mistake in the video, don't worry, we'll get back to it later. We connect these two results to the start and end of the line trace and then drag out the trace's return value into a branch. We also split out the struct bin. If there is no hit, we're going to return an empty hit location, a line rotator and foot distance to ground value. These are a vector, rotator and a float respectively. We add another branch and we will break the hit location vector to get the z value and compare it to our foot location z. We also subtract the two z values and take the absolute value of that to return our foot distance to ground if the hit location z is above the foot z. Then we drag out the hit factor to our hit location return, and finally drag out our out hit normal to break it. Use two 8-10 nodes to calculate the desired foot rotation on uneven surfaces and set that rotator as the return value. I'm not going to dive too much into the math, so just trust the video for now and calculate it yourself later if you wish to do so. We now head back to the foot IK function and drag in our new trace function. We first do the left foot using the XI from the socket and Z from the skeleton. We then create a rotator variable for each foot rotation L and R respectively, as well as a foot IK effector L and R variable. We add these variables to the category foot IK to organize things a bit and set the rotation vars to rotators and the effector ones to floats. In the foot IK function, we use our trace results aligned rotator for the foot rotation variable and the distance to ground for the effector ones. We repeat what we just did for the left foot and for the right foot as well. When finished, head back to the event graph and drag in the foot IK function, connect it to the event flow and head into the anim graph. We're going to want a neutral pose as a base idle animation so we don't get any animations that don't line up with our real life movement. So to easily get that, we head into the skeleton view and export the current pose as an animation. We call this animation anim_hands open. When we work on hand animations some other time, we can make a closed pose animation as well to blend between the two. We use this new animation as output pose for now and navigate to content, advanced locomotion v4, character assets, mannequin skeleton animation examples. Here we will select all run and walk animations as shown. And right click, retarget, animation assets, duplicate and retarget. In the retarget menu we uncheck show only compatible skeletons and on the left select our mannequin skeleton. We click change folder on the right and navigate to mannequin animations, then on the left click retarget to finish the retargeting process. Navigate to the new assets, quickly select and save them all, and then right click to create a new blend space. We select our mannequin skeleton here once again and name this asset BS_VR_player_walk. In the editor, set the horizontal axis to be named direction with minimum value -180 and maximum 180. The vertical axis will be speed with minimum -2 and maximum 2. We then drag in our anim_hands open into the center of the grid as a base pose and then arrange our walking and running animations as shown in the video to get smoothly transitioning animations in all movement directions. When finished, we head back into the animation blueprint and right click to add a state machine. We name it default. Double click it to go in and add a new state named idle/walk/run. We don't do much else with this state machine, but this is generally standard in animation blueprints. We double click the state we created and plop in our Blendspace as an animation. Now we need to get some speed and direction values, so we head to the event graph, add a branch and get the speed and direction from our VR player, store them as variables, and try to somewhat organize everything before going back into our Blendspace and plugging in the values. We then replace our single animation on the anim graph with this new state machine output. Next up, we're adding two vector variables called joint location L and R respectively, which we also add to the food IK category. And for their default values, you can copy the ones used in the video. You can figure these out in the skeleton view, but that's a topic for perhaps another video. Then in the anim graph we create some space and add two bone IK nodes. We drag our pose into the component pose slot, which automatically converts it, and drag in our effector and joint locations. We create vectors from the effectors and all of it gets connected to the two bone IK nodes. One for the left foot and one for the right foot. Now what's important is to pay attention to the config of the nodes. We want to select the correct foot bone as our IK bone, set maintain effector relative rotation to true, set our effector location space to bone space, and set the newly appeared take rotation from effector space to true. The effector target will then be foot bone once again. For our joint target, we set the parent bone space as location space and actually select the thigh bone, either the left or the right one depending on the foot, as our joint target. Make sure to do this carefully for both two bone IK nodes and not to mix up the right and left bones or variables. Now we head into our VR player, select the skeletal mesh and set it to use our animation blueprint. Then we jump to the calculate movement function and create some space to drag in our distance rotated and add this up with the distance moved. Then divide it by 2000 and connect it to the division node. Lastly, jump back to the trace ground function and remove the extra minus I added there by accident if you followed along with that mistake. Now we create some space near the end of the anim graph and add in two transform bone nodes in which we will apply the foot rotations. In these nodes we set the bone to modify the feet bones and set rotation mode to add to existing enrolled space. Do this for both nodes left and right respectively. Then we drag in our foot rotation variables and connect them to the correct node. Now we make some space on our right foot effector and multiply it by -1 to fix its direction. Compile both the character and the animation blueprint and give it a go. Your feet should be on the ground nicely now. Now it's finally time to finish it all up by adding hand and hat tracking. First I will do a bit of cleanup by creating a comment to an animation blueprint and then create some space. When done, I add a fabric node, 2 transform bone nodes and 2 2-bone IK nodes. Then I once again create some space and drag in the VR player to get the camera world transform. Simply plug the world transform into the fabric node and connect the component post to the node as well. Then break the transform and add a combined rotators node with which we will adjust the rotation of the camera. And as I'm running out of workspace, I'm going to move around things once again, as well as add in another transform bone node. We drag the modified rotator into this bone transform node and set the node's rotation and translation to disable, as well as the bone to modify to our head bone. This takes care of all head animations. We then get the VR player once again, organize our IK nodes and get both the motion controller world transforms from the VR player. We break these and drag their locations to the effector location of the 2-bone IK node and the rotation to the transform bone node. On our right controller we adjust the rotation by 180 degrees on the Z-axis, and for our left controllers it's 180 degrees on the X-axis. We now finally have all the nodes we need, so it's time to organize this mess with some comments and post caching. This is completely optional, so if you wish to organize things similarly to me, feel free to follow what the video does, but I'm speeding things along to get back to the actually important stuff. Now that everything is organized, we can hit compile to see some warnings we have to attend to. So first we will get rid of our direct calls to the VR player and move that into the event graph instead. We create transform variables for the head and hands and set their values. Then we head back into the enum graph and connect our variables to the IK nodes. Then when that's done and I've satisfied my need to excessively organize and color code, we will head into the modified bone node for the head and set it to replace existing in Worldspace. Then we head into the hands 2 bone IK nodes and set the IK bone to the correct hand and the effector location space to Worldspace. Then we go to the transform node and set the bone to the correct hand there as well, set the rotation mode to replace existing and set it to use Worldspace here as well. We do this for both the left hand and the right hand naturally. We should now be able to compile or see our hands look super weird. Now, as the last step, we have to set the hand joint locations. Again, here just follow along with the values I type into the left and right hand nodes, then save your work and give it all a go. And this will conclude the tutorial. I hope this is helpful to anyone at all. It was a pain to make, quite honestly. It's my first tutorial ever. I had to shrink down 3 hours of footage, record myself time and time again, shrink down the script, figure out how to make this comprehensible. So yeah, if this was in any shape or form helpful, please let me know. If there's any critique, please let me know so I can improve. And I hope to maybe see you in the future if anyone is interested in seeing more. Thank you so much for your time. Have a great day.